The Doppler effect. The best example of the Doppler effect would be a race car at a racetrack. If you've ever been to a race track, the cars make this weird sound. It almost sounds like vroom, vroom, as they zip past. So when the car is approaching you, it's a much higher pitch. Once it passes, it's a much lower pitch. So that's what we call the Doppler effect. So when a source of sound approaches an observer, in the case of a racetrack, the source would be the car, you're the observer. The observed frequency increases. That's the higher pitch that we hear. When the source moves away from the observer, so that means once the car is past you, all of a sudden the frequency decreases. You hear like a lower pitch. So I have a diagram here trying to explain this phenomenon. So if whatever is making the sound is stationary, so it could just be someone like hitting their horn in their car. So if the car is stationary, it's hitting their horn, we have an observer here at position A and an observer here at position B. And what happens is they hear the exact same thing. We have the horns making the sound, and we get these little circles that move out away from the sound, and A and B hear the exact same thing. Now, the interesting part is, well, what if that car started traveling towards observer A? So it starts moving to the left. Well, it's traveling in the same directions, making the sound waves. So it's catching up to them a little bit. It's not passing, but it's getting closer. So all the sound waves here become compressed and closer together, which gives you a higher frequency. Also, well, there's more space now between the source of the sound and observer B. So because these are further apart, we end up with a much lower pitch that we hear. So when something's going towards you, higher pitch. Away from you, lower pitch. So here's a little summary. So it says, object moving towards you, the wavelength decreases, but the frequency increases. Also, if the object's moving away from you, well, the opposite happens. The wavelength increases and the frequency decreases. To solve for this frequency discrepancy, where sometimes it's higher pitch, sometimes it's lower pitch, we have this formula here. So frequency 2 is equal to frequency 1 bracket V divided by V plus or minus V of the source. So let's go over what these things are. F2 would be the frequency that you're hearing. Okay, so sometimes it sounds higher pitched or lower pitched, depending if the object's moving towards or away from you. Frequency 1 is whatever the frequency is being made by the object if it was stationary. So if it was stationary with hitting their horn, that's the frequency that they're producing. V is simply just the speed of sound in air. V source is the speed of the object. So if it's a car driving, hitting their horn, if they're driving at 80 kilometers per hour, well, that would be the speed of the source, except you have to change it to meters per second. Now, the plus or minus is determined by if you're moving towards the object or away. So if the object's moving away from you, then we put the plus in. If it's moving towards you, we put the minus in. So the only difference if they're moving towards or away is this plus or minus. Let's try this example here. It says a car traveling at 100 kilometers per hour. So that's how fast the source is going. So we know V of the source is equal to 100 kilometers per hour. There's a problem here. This is in kilometers per hour. I need it to be in meters per second. So I would times it by 1,000 divided by 3,600, and I get 27.7 meters per second. Let's keep reading here. Sounds its horn as it approaches a hiker standing on the highway. The car's horn has a frequency of 440 hertz. So even if the car was stationary, no one's moving, that's what the frequency 1 is going to be. That's the frequency of the horn all by itself without becoming higher or lower pitched. So we know frequency 1 is 440 hertz. The temperature of the air is 0 degrees Celsius. We know that whenever we're given temperature, we can actually figure out the speed of sound for that day. So our formula for speed of sound is this. We have V is equal to 331.4 plus 0.606 times the temperature. Well, that day the temperature is actually 0 degrees. So simply The speed of sound for that day is 331.4 meters per second. And then it says, what is the frequency of the sound reaching the hiker? So as the car approaches, when it approaches, okay, that means it's coming towards you. We're going to use the minus sign. We're going to use, can't see that? We're going to look at the minus sign. So I'm going to say towards, and I know that means I'm going to be using the V minus Vs. So let's put all this information in. It's a giant formula, so it's F2 is equal to F1 bracket V over V, in this case will be minus V of the source. Plug in everything you know, so it'll be 440. V we calculated to be 331.4 over 331.4 minus 27.7. And when you put that into your calculator, you end up with 480 hertz. The other thing you need to do is think about this. Well, if it's coming towards you, we should have a higher pitch than if the object was stationary. And we actually did end up with a higher pitch than when the object started or was stationary. So we did it correctly. Let's solve part B now. So after the vehicle has passed the hiker, well, that means now it's traveling away. And we know when it's going away, we want to use the plus this time. So it's going to be V plus Vs. And the rest of the problem is exactly the same. It's very straightforward. So we know that F2 is equal to F1 bracket V over V minus, plus Vs. Plug in everything you know. So this time it's going to be 440. 331.4 over 331.4 plus this time 27.7. When we put all the information to your calculator, you should get 406 hertz. Now let's think about this. When an object is moving away from you, it has already passed, we should hear a lower frequency, and we do. You'll actually hear 406 hertz instead of, when the object's stationary, 440 hertz.